So welcome to everyone to Coffee Buddies. We're part of the Biotech Gate Festival, and it's always a pleasure to be here. And our modus operandi as Coffee Buddies is to entertain, engage, and inform. And we're very lucky tonight to have a good friend of mine called Raminderpal, who will be talking about a very interesting area, which is very close to my heart, which is causation. Raminderpal, first of all, maybe you could introduce yourself, say where you are, who you are, and what you do.
Sure. So I'm sitting in London. Actually, I spent most of my business life in the States. Worked in San Jose, then Vermont, and then New York. I worked at IBM. Came back to London about a decade ago. I actually live up in Manchester. And so I've done a bunch of, my PhD's in semiconductor engineering, but I did a bunch of stuff there. Then I moved over to do Watson Genomics, took Watson Genomics to market for IBM. And then I came back and I did some, straight sales stuff for some Eagle Genomics. Currently I run this company which works on causal. So it's really a pleasure to talk to you guys. And funny enough, injury is one of the topics, brain injury really actually, because we do, our internal program is actually Alzheimer's. And so when you get into those sort of CNS neuronal type stuff, you really start thinking about endpoints like that. But it's
exactly. And you've got a few slides because it's an area that is fascinating and needs more careful navigation. So maybe you could bring up a couple of your slides or bring up your slide deck.
All right, let's see if this works for you guys.
Yeah, I think that's it. And I mean, let's start with causal analysis, the solution to AI drug discovery. What a wonderful set of words. Maybe you could explain a little bit more.
Okay, so causal analysis is a term which is often used. I mean, the fact that we talk about causation and cause and effect, this and that, has been going around for decades, hundreds of years. But causal analysis itself is a formal method. And it's not the way we think of it, like I run a whole bunch of combinations and then I can work out which combinatory, which parameter is the right parameter. It's actually a formal method. It's a Bayesian method, which, funny enough, is used in a lot of industries these days. And we're the laggards in life sciences and healthcare. So it's used in day trading, social media, Microsoft Research use it, retail use it, marketing use it. But in science, things are always harder, right? So it's been dragging. So whether you're doing drug discovery or even other things where there's biological mechanisms in a broader sense, causal analysis has yet to be brought to the table. And that's what I'm keen to evangelize here.
And there's this individual, which is on the next slide, which you're going to bring up.
Yeah, so...
which is Judah Pearl, who... Oh, you've got a slide before that.
Yeah, so always good to start with the Dilbert. I just thought that'd be nice. I don't know, you guys... You must have heard that the bumps and knocks of correlation is not causation, but that's very real. And for everybody on this call, you'll be living correlative environments. I do machine learning, I do AI, but you'll be finding it really hard to take actions on it. So the notion of actionable insights is a bit of a false domain. But this is the slide which you're referring to. This gentleman here, his name's Judah Pearl, UCLA. Took some of the Bayesian theorem work, which had been done over hundreds of years, as we know about, and he created Bayesian networks, and then he formalized that to this term. It's called Pearlian causal inference. And then there's been so many spin-outs. CMU do a lot of work on this. They have an open source library on this, Microsoft Research, IBM Research, and they've captured the notion of doing this Bayesian method, and they've captured it. And what we're doing is we're looking at, okay, fine, but how do you apply this method, which this gentleman has applied, for many decades, and Turing Award is a very big award to win. How do you take that and how do you apply it with biological data and biological mechanisms, discovery and simulation?
So, I mean, and if we maybe move to the next slide. So just, I mean, from my point of view, that there are a number of elements that we have to take into account, and then the application of this causal analysis on those many elements. Is that correct?
Yes. So as biologists or chemists, we were talking earlier, things are much harder. The nuances matter. The nuances in the data matter. The nuances in previous prior knowledge, literature matter. And we have to learn to be able to absorb these components, because with these Bayesian methods, prior knowledge matters. It's not a black box method. Look, show me the data, I'll run it against some neural network or some sort of trained algorithm, and it'll spit out some correct predictions. Real life doesn't work that way. Scientists don't operate that way, and causal analysis doesn't operate that way. It takes, as you can see on the left-hand side, takes knowledge, takes literature, takes previous study data, and even takes results which are coming from ML and AI, and it churns that, and it creates a more let's say a more knowledgeable or more biased, but a more specific model, which can be used. And so those nuances are very hard to do. And that's the game. The game is to take the generic methods and to make them applicable in our worlds.
So in a simple way, it's a bit like a very knowledgeable expert who's got all these templates in their head, wisdom templates. Really what you're doing is sucking a lot of that knowledge out of the literature and then allowing you to bring that into the calculations. Is that the idea?
Yeah, no, this is well said. And I think it's something you've mentioned before to me when we've been talking about this. If you take a KOL, a key opinion leader, and they have decades of experience. Of course, some of that drives some bias. And then you've got lots of literature, which of course has some, false positives in it, because that's what, people are publishing everything. But if you mix those up, how do you get to a point where you have some really good golden knowledge, which you can structure and then do some hypothesis testing on, turn it over and see what it spits out?
Yeah. And that's this concept of, if you read 3 papers, that if you're a person who's knowledgeable, you scan it, you, if you like, run your own reference points to all the knowledge you've got in your head, and then out of those reference points you come up with experimental hypotheses. That's what you do every day. And what you're saying here is you can do this in a more systematic way. Yeah,
we can systemize that. We can turn it into a model. I mean, it's a model. At the end of the day, it's computers. It's in silico. And not only can we turn it into a model, but we can even play with that model. We can, toggle parts of that model, and that creates this kind of in silico experimentation. So not only you understand where the drivers could be, but you can play with it and see, okay, for example, the brain injury example. If I'm playing with proteins, how do they affect endpoints? How could they affect endpoints without running, very expensive experiments or studies or clinical trials even? How can we do these things and find points where we have confidence, and then aim those experiments, those trials, where the confidence is strong?
Excellent. Okay. So, and you've got here that biological experiments are made cheaper, faster, cheaper, and better with causal analysis. Do you want to say a little bit more about that?
Yeah, so part of this is evangelizing. The world is in classical methods. People talk machine learning, AI, and frankly, those are things you learn at school, and those are what we call classical statistics. Trying to move things over to Bayesian thinking, which is prior knowledge, is very valuable. You use it, it's very valuable. So if you have that prior knowledge and you turn it into a model, and you use that model to filter out things, to rank order things. Computers are free, storage is free, compute and all these things are at our fingertips. Then when you go to the blue boxes, when you go to the wet lab design, you have a much better place. That means that your iterations on the blue boxes, your wet lab experiments, much faster. Your clinical trials are much better designed. Your starting points, your cohorts, your hypotheses have much more confidence in them. Makes them faster, means less iterations, makes them cheaper, and you get better results, because the thing about computers is they can look in large spaces. Unfortunately, if we are often limited in our wet lab experiments to iterations, but it's very difficult to have an experiment over here and a completely different experiment over there. It's very hard to run a program like that. But if you can find the right starting points, then you can iterate through your wet lab experiments and you can have better results as well. more novelty, more new thinking, which is, of course, we're seeing with Alzheimer's, where people are trying to get off beta and tau. You can do that, and you can shift that in the way you think about things. And again, using injury as the example.
Which I think is really interesting, because, I mean, this idea of a knowledge graph as a, do you want to say something about what a knowledge graph is? Just
yeah, so we're used to, if you look at the growth of knowledge over time, when SQL and tables and relational tables started appearing in the 70s and 80s, the amount of knowledge expanded in a huge fashion. But if you look now today at data science, there's something called graph databases, which is where instead of the information being in the nodes so much of the information, like, or the cells of a table, they're in the actual connection, the relationships between information. And that's very popular now. And you see a lot of companies using knowledge graphs to the correct thing. The question is, how do you use that? How do you explore it? And how do you find confidence of where to tap in the knowledge graphs, so you can go spend money on things like experiments and trials and things like that?
Yeah, very interesting. Next slide, my friend.
Sure. So just as an example here, guys, I think it's very important to land this a little bit. So we want to show a little bit of work we've been doing on diabetes, all in silico. We're not a diabetes company. In fact, our main publications are on neuronal degradation, pointing at, CNS and, ND type neurodegenerative diseases. But we've got some work coming out, and in a couple of weeks' time, we're going to put a pretty good paper out on bioRxiv. So please reach out to me, get a copy of the paper. It's good work. So there's a lot being said here, and for a lot of folks on the phone, you will really appreciate this, and for others, maybe this is a little bit new. The grey picture is taken from literature. The grey picture says, look, we do understand type 1 diabetes quite a lot, but we understand it from a sense of, we think we know what's going on, because this is not, you don't have all the phenotypical endpoints ready to, the measurements. This is inside the actual pathways. This is the stuff you can simulate, you can emulate, but you don't really know truth. So you need to be able to hypothesize and test your hypotheses. And that's where Bayesian methods like this really come into their play, when done right, of course. So read the red text. The red text is the important text. So we wanted to be able to look, what are the drivers, and separate the drivers, so you can understand a little bit about what are the key, the strengths of effects, we call them, in these mechanisms. The mechanisms are known, but what's really pulling and pushing in these mechanisms? Where are the things that you should worry about and the things you shouldn't worry about? And you can see in the bottom on the left here, this little blue diagram, we've got known, and we've got those affected by type 1. And then we can measure type 1 progression. So there's always an endpoint, some phenotypical, some physiological stuff we can look at. And at a simple level, if you do some associative analysis, your AI, your ML, you can see some correlations. They can highlight things that are possible, but they don't really separate what's going on and allow you to make clear hypotheses, or have confidence in hypotheses, or rank the confidence in hypotheses, to allow you to go ahead and say, okay, maybe I should drug some of this over here instead of over there. But if you look at the bottom, we're able to do that. And the paper we'll be pushing out talks about this in much more detail.
Which is really interesting. So you're sort of untangling the complex system shown in the KEGG pathway, and trying to understand which are the important parts. Is that right?
Yeah, so the way to think about it is you download KEGG, and for folks who, KEGG's kind of a well-accepted protein pathway database. You download, you get relationships, and these relationships are being curated over time. Yeah. They tell you relationships exist or potentially exist, but it's fairly good work, but they won't tell you in what fashion, where the strengths are. And they also won't allow you to, of course, to simulate, if I change some proteins, what happens, or say change the weight, the size or the quantity on a driver, on a protein driver. So we're able to enrich KEGG information. So now that becomes truly actionable. And it's very complicated. Biology is very complicated, especially if you get to diseases and processes which are, out there as opposed to mainstream. This is diabetes, a bit more mainstream. Some of the work we're doing is very complex on some very rare diseases. But you can put the pieces together and then you can run these hypotheses testing, and then you can look at that and go back to literature and just say, hey, this makes sense. We didn't realize that this could be a driver based on some other proxy information in literature. And that sort of Sherlock Holmes building bricks approach really changes the game for scientists.
Well, that's the thing. I mean, if you take that pancreatic islet block at the top, this is the question where you've got a set of proteins and you want to be able to ask the question, which are the important ones? And is the point really, that you can start dissecting this diagram and get more of an understanding of importance.
You not only get importance, but you can also then toggle those important ones, the value on them, and then simulate, okay, so how do they affect endpoints?
Yes, yes.
And you can do all that, on a computer.
Yeah.
And in fact, it doesn't require much of a computer to do it, because this sort of mathematics is not big data in the sense that it doesn't require big servers to do.
Yes. I mean, this is the interesting thing for the sector, that, if you think that you've got multiple targets, so you've got, so many companies that will be doing multiple targets. And, the question always is, which ones are the more important ones? And everybody has their own bias. And the question is whether you can punch through the bias.
Right, and it takes on the question about data-driven conversations. Everyone likes to say, well, we'll listen to the data. But then they come and say, well, here's my personal preference. So if you're able to draw a simulation out, draw an analysis and a simulation out, which everybody agrees, okay, we're going to run that, and we're going to look at that, and we're going to come together and discuss based on that data of that simulation, then you actually make decisions a lot easier, a lot more consensus.
I love that. Next slide, my friend.
That's it for me. There is a call to action. I really appreciate this. A great audience here today. We're talking to scientists, we're talking to investors. We're a company here. There will be folks on the phone here. There'll be folks listening to this recording who will say, look, yeah, but I have some causal questions. I have mechanisms I'm looking at. And we're talking to people in bioactives, we're talking to people in agri-tech, we're talking to people doing drugs, med tech R&D. Wherever there's these mechanisms you're looking at, please give me a ring. It's really interesting conversations.
Well, Raminderpal, I mean, that was terrific. And I just love all this. Graham, do you want to take, Raminderpal,
yeah,
do you want to take the slides down?
If you take the slides down, Raminderpal, and then we'll just see.
But thank you very much. That was terrific, and an area that I find fascinating, and I'm sure everyone does. So I think before we do any moving out, we should do some questions, because I think it's a very hot topic. Have you turned the recording off, Graham? Yeah.
I'm going to turn the recording off now, so we can just.
So let's do